Today we'll be discussing 12 Amazon Elastic File System, or EFS, Microstacks. Subscribe to the channel and like this video for more great cloud tips. Strip away the marketing name and Amazon Elastic File System is just a network file system in the cloud. The interesting part is everything that becomes possible once other AWS services read and write to that same file system at the same time. A single shared elastic volume means an EC2 fleet, a set of containers, or a swarm of Lambda invocations can all work from one consistent set of files. That beats juggling copies, sync jobs, and stale data. Get the surrounding architecture right, and that shared storage layer becomes invisible infrastructure that just works. It scales capacity up and down automatically while every compute resource sees the same files. Mess it up, and you end up with permission conflicts, throughput bottlenecks, or a storage layer nobody backs up until it's too late. A microstack is a reusable combination of two or more cloud services. Let's walk through 12 microstacks, proven service combinations and architecture patterns for Amazon EFS. They show how EFS pairs with compute, networking, orchestration, and security services to deliver storage that's fast, durable, and safe to depend on. 1. Mount EFS across EC2 fleets for shared, durable file storage. Mounting EFS across an EC2 fleet gives every instance the exact same files to work from. EFS presents a standard NFS-compatible file system that any number of instances can attach to at once. EC2 supplies the compute. EFS supplies storage that grows and shrinks automatically, with nothing to resize by hand. A file written by one instance shows up instantly on every other one. This shows up constantly in content management systems and shared web tiers. Place mount targets in every availability zone the fleet spans so instances always reach storage over a low latency path. 2. Stage large S3 files through Lambda and EFS for serverless processing. Lambda hits a hard wall the moment a job needs more space than its own temporary storage allows. Attaching EFS removes that ceiling, giving the function a persistent, expandable file system to work in. S3 holds the large files like video, genomic data, or ML models that need heavier processing than Lambda's limits permit. Lambda pulls a file from S3, uses EFS as scratch space, then pushes results back. This fits media transcoding and machine learning inference on files far bigger than a typical payload. Keep the EFS access point scoped tightly to the function's execution role. 3. Attach EFS to ECS containers for persistent concurrent container storage. Containers are supposed to be disposable, which breaks down the moment data needs to survive a restart. ECS handles scheduling, while EFS gives those containers a shared volume that persists on its own. Multiple ECS tasks can mount the same EFS file system at once, each reading and writing safely. That turns a stateless, ephemeral fleet into something that can run real stateful workloads. It's a strong fit for shared upload directories and containerized content systems. Use EFS access points to scope each service to its own subdirectory, so services don't step on each other's files. 4. Scale EC2 with autoscaling in EFS for elastic shared storage capacity. A fleet sized for peak load wastes money the rest of the time. Sized for average load, it falls over under a spike. Autoscaling adds and removes EC2 instances automatically as real demand shifts. Why does every new instance need the same data as the rest of the fleet? Because new instances mount the existing EFS file system automatically at launch, with nothing to copy by hand. Because EFS scales its own capacity too, storage never becomes the bottleneck. Bake the EFS mount command into the launch template so scaled-out instances attach storage on their own. 5. Monitor EC2 and EFS with CloudWatch for proactive storage operations. File system that quietly runs low on burst credit turns into an outage nobody saw coming. CloudWatch collects metrics from both the EC2 instances and the EFS file system itself. EC2 contributes CPU and instance health. EFS contributes throughput, IOPS, and burst credit balance. Together they show whether a slowdown is compute or storage. Storage problems and compute problems look similar from outside but need different fixes. Set an alarm on EFS burst credit balance well before it reaches 0, since credits recover slowly. This video is a condensed version of what we have on systemsarchitect.io. See the full section there. Also be sure to like the video and subscribe to the channel for more, and check the video notes for links. 6. Deliver ECS content through CloudFront and ALB with EFS for global reach. Serving content globally means getting requests to the nearest edge and then to healthy backend capacity. ECS runs the application logic, while EFS gives every container the same underlying files. And ALB distributes requests across running tasks and routes around any task that fails a health check. CloudFront caches content at edge locations worldwide, so repeat requests never travel back to the origin. EFS keeps the origin consistent, ALB keeps it healthy, and CloudFront keeps it fast. Set cache behaviors deliberately for dynamic versus static paths so personalized content still reaches the origin. 7. Orchestrate Lambda and EFS with step functions and S3 for multi-stage processing. Some jobs aren't one function call, they're a sequence of stages, each depending on the last. Step functions coordinates that sequence, with retries and branching built into the workflow itself. S3 holds the source data and the final results moving through the pipeline, what lets every stage skip re-uploading files through S3 each time. EFS does, by giving every stage a shared, persistent working directory instead. That shared workspace cuts out redundant data movement between stages. Clean up scratch files at the workflow's final step, since storage that's never cleared keeps growing. 8. Sync and protect EFS with data sync and backup for hybrid resilience. Moving data from on-premises storage into the cloud, then protecting it, are really two separate problems. Data sync handles the first half, transferring files from on-premises systems into EFS without fragile scripts. EC2 instances then access that data directly, just like it had always lived on local infrastructure. AWS Backup takes over from there, creating recovery points on a schedule and retaining them by policy. A corrupted file or an accidental deletion is always recoverable this way. Tag EFS file systems by workload so backup policies can vary between critical and non-critical data. 9. Run stateful EKS workloads on EFS with ALB and CloudWatch for Kubernetes storage. Kubernetes assumes pods are disposable, which is a real problem when data needs to outlive the pod. EKS manages the cluster and schedules pods across nodes. EFS closes the persistence gap, giving pods a volume that survives restarts and even node failures. And ALB handles ingress, routing traffic to the right service no matter which nodes are running it. CloudWatch closes the loop, surfacing both cluster-level and storage-level metrics. Use EFS access points per namespace in multi-tenant clusters so different teams' workloads stay isolated. 10. Bridge EC2, EFS, and FSX across Transit Gateway with data sync for multi-region access. Large organizations rarely settle on one storage system and rarely stay in one region either. Transit Gateway acts as the hub connecting multiple VPCs across regions through one manageable point. EFS and FSX sit on either side, each serving the workload it fits best. EFS for Linux, FSX for Windows or high-performance file systems. Why does that split matter for a large enterprise? Because data sync moves data between them and keeps both sides synchronized, so nothing drifts out of date. EC2 instances across connected VPCs then reach whichever storage system matches their workload. Document which VPCs are authorized to reach which storage systems, since a hub this size can make unintended access easy to overlook. 11. Trace ECS and EFS with AppMesh, X-Ray, and CloudWatch for observable microservices. Once an application splits into a dozen microservices, understanding why a request was slow gets hard fast. ECS runs the services as containers, while EFS gives any of them that need it persistent storage. AppMesh adds a service mesh layer, standardizing how services discover and talk to each other. X-Ray then traces individual requests as they hop from service to service. CloudWatch ties it together with broader metrics and logs. Instrument X-Ray at the application layer too, since mesh-level tracing alone won't catch slowness inside a service's own code. 12. Secure Lambda and EFS behind API Gateway with Cognito and Web Application Firewall for protected file APIs. Exposing file storage through a public API invites unauthenticated access, bad payloads, and denial of service traffic. API Gateway sits at the front, routing authenticated requests through to back-end Lambda functions. Those Lambda functions access EFS directly, reading and writing files as part of serving the API. Cognito verifies who's calling and what they're allowed to do before a request reaches Lambda. Web Application Firewall filters out common exploits and bad bots before they even reach the authenticated part of the stack. Scope Cognito authorization down to specific routes so a single compromised token can't reach every file operation. Thanks for checking this out. Hope you learned something. Find a lot more articles and guides on both systemsarchitect.io and codeguides.io.